Swayam Prabha. Digital India. Educated India.
Today I am going to discuss some typical problems of vibrations. In the last 4 lectures we have been discussing about the vibrations of single degree freedom system. We have formulated the differential equation by applying Newton's law or D'Alembert's principle. Also, we have discussed about energy approach of obtaining the equations of vibrations, or equations of vibrations, or frequency of vibration. So, there today I am going to discuss few problems, and some of them of advanced nature, and some simple applications of the vibrations. So, we discuss with the case of a simple pendulum. Again, let us see, we have already discussed simple pendulum. This is a small bob is attached by a string, then this is moving in a circular path. This is the next position, okay, that can be like this here. Now, this angle is theta. So, the next position which I will show like some dotted line. So, this is the next position, okay, chain dotted type thing. Now, what is the equation of motion for this? Equation of motion can be obtained by I theta dot equal to net torque about O, and I is about this one. So, here I will be equal to, if this is the length is L, I is equal to m L square, and then there is a force acting on the bob is m times g, then there is a tension of the string, that is T. mg can be resolved into two components. One is mg sin theta tangential to the that circular arc, and other perpendicular component, that is mg cos theta, which is in the direction of the string. So, if you take the moment about O, then T or mg cos theta will not contribute to moment, only mg sin theta will be contributing to the moment, and that moment is mg sin theta into L. Well, this is the thing. So, mg, therefore, and it is directed in the direction opposite to theta, because it is directed like this. So, it is basically clockwise, because if you just place yourself on this line, look towards 0, O point is towards right hand side. Therefore, you get the equation I theta dot dot, that is equal to ml square theta dot dot is equal to minus mg sin theta multiplied by L. So, m and L can be considered from both sides. So, this is then this equation becomes theta dot dot plus g by L sin theta is equal to 0. This is the exact differential equation of the simple pendulum. However, we make assumptions that for small amplitudes sin theta may be regarded as equal to theta. So, therefore, equation becomes theta dot dot plus g by L theta equal to 0, and this can be compared with mx dot dot plus kx equal to 0 spring mass system. So, you get the simple harmonic solution of that, but that is the approximate. Let us see that how the analysis can be done for exact vibrations. Now, in case I cannot neglect, I cannot consider theta to be very small. So, theta dot dot plus g by L sin theta is equal to 0. How do we solve this differential equation? This differential equation is a non-linear. If there is some solution, suppose x is a solution of this, that does not mean a constant time x is a solution of this. This is a non-linear differential equation, and for solving it, multiplied by theta dot. So, theta dot theta double dot plus g by L sin theta theta dot equal to 0. Let us multiply by 2. So, this is 2g sin theta, this is the thing. Now, we want to integrate this equation. Now, let us integrate this equation between position of maximum amplitude, maximum displacement, that is the last point of the amplitude. Now, theta, so this will be that time. So, at theta m, let us say theta m is the maximum displacement. So, at theta m, theta dot must be 0. Now, integrating it, theta m theta 2 theta dot theta double dot. So, initial position is theta m, final position is any arbitrary theta, plus theta m theta 2g by L sin theta into theta dot is equal to 0. Now, if if you integrate this and put the limit, so this will be d theta by dt whole square minus d theta m d theta by dt d theta at m by dt, that means derivative at m, but that is 0. So, therefore, I am rubbing here itself, this is not required. This is d theta by dt square, this one, and this thing will become equal to plus now 2 sin theta dot, this can be written integrated. Okay, this is, I must put an integration sign here, dt, this is integration sign dt, then it becomes that complete. This is equal to 2g by L cos theta minus cos theta m. So, integration of this comes out to be cos theta minus cos theta m, this is the thing. Now, cos theta can be written as 1 minus 2 sin square theta by 2. Similarly, cos theta m is equal to 1 minus 2 sin square theta m by 2. Therefore, cos theta minus cos theta m actually becomes 2 sin square theta m by 2 minus sin square theta by 2. So, now you have got the expression d theta by dt whole square is equal to 2g by L cos theta minus cos theta m. In place of that, this can be written as 2 times sin square theta m by 2 minus sin square theta by 2. So, therefore, d theta by dt can be written as 2 under root g by L sin square theta m by 2 minus sin square theta by 2 in bracket, that is square this one, and now therefore you can write that d 2. Now, therefore, this can be written as dt is equal to dt d theta divided by 2 sin square theta m by 2 minus sin square theta by 2, then under root L by G. Now you can integrate from t is equal to 0 to theta equal to t is equal to t by 4, where t is the, so integrate from t is equal to 0 to t is equal to t by 4. Here then at t is equal to 0, theta is equal to 0, and at t is equal to t by 4, where capital T is the time period, theta is equal to theta m. Doing this, we obtain t is equal to 2 under root L by G 0 theta m d theta by sin square theta m by 2 minus sin square theta by 2. This cannot be further simplified. So, this integration cannot be determined in an exact manner. It can be determined numerically. This integral is called elliptic integral. One can use the expression sin theta by 2 is equal to sin theta m by 2 sin phi. This type of substitution can be implied so that limits change from 0 to theta m to 0 to pi by 2, because at phi equal theta equal to 0, phi is equal to 0, at theta is equal to theta m by the theta m, sin phi is equal to 1, that means phi is equal to 0. So, therefore, time period t can be written as 4 under root L by G 0 to pi by 2 d phi under root 1 minus sin square theta m by 2 sin square phi. Now, this has come, this type of integration has come in some standard form, because limits are 0 to pi by 2. Now, the value of the integral depends on the value of theta m. These values have been tabulated, which I am not showing here, but they are available in any book of mathematical tables. Here, that these values of the integral have been tabulated, and it is observed that up to 10 degree, whatever time period is obtained by taking the assumption of sin theta equal to theta is almost same as this one. So, up to 10 degree simple harmonic motion approximation is reasonably accurate. After that, one has to go for the exact analysis, and this is what that this example has shown. Okay. Now, I will take up the other example. Now, here another simple example. If this is there is a, let us take a simple square plate, thin square plate, which is hanged from this point. This is the G mass center, then this distance is B, this is B, this is 2B. Now, if axis of vibration is passing through this point O and is perpendicular to the plane of the paper, what happens? Now, when this is rotated, this will become like this, small let us say I have given theta angle. And therefore, that time the G will be rotated by theta. So, therefore, a vertical line passing here, but this G has gone to this point. Therefore, this is theta, this is the weight is W. Therefore, there is a tangential component, that means G moves in a circle, draw a tangent at this one, find out this component, that is my W, that is W sin theta. If you take the torque moment of this about this point, that will be W sin theta into B. It is clockwise, so it has been shown. That must be equal to I0 theta double dot, where I0 can be found using the parallel axis theorem. For this plate, moment of inertia about the mass center G is Ij is equal to 1 by 12 m, m is the mass, 2b square plus 2b square. It is Ij is basically Izz, z is the perpendicular to the plane of the paper. So, this is Ix plus Iy. So, half m 2b square, which comes out to be 2 by 3 2 by 4b 8b. So, it becomes 2 by 3 mb square. Now, parallel axis theorem can be used. So, therefore, IO will be 2 by 3 mb square plus m times b square. Total mass is m, distance from G to O is mb square. So, therefore, this can come equal to 5 by 3 mb square. Now, Therefore, equation becomes 5 by 3 mb square theta dot dot is equal to minus, restoring thing, minus w b sin theta is equal to minus mg b sin theta, or theta dot dot plus 3 by 5 g by b sin theta is equal to 0. However, for small theta, sin theta is approximately theta, provided theta is measured in radian, not in degree. So, sin theta, so one has to be careful about this, sin theta is equal to theta, provided theta is measured in radian. Then theta dot dot plus 3 by 5 g by b theta equal to 0, or this can be compared with mx double dot plus kx equal to 0, for which we know the frequency under root k by m. Same thing happens here. So, therefore, omega will be under root 3g by 5b, and time period can be written as 2 pi by omega, that means 2 pi under root 5b divided by 3g. So, that means more is the size of this one plate, more time is required. So, this is about this. Now, similarly, let us discuss some other problems. Now, I will take up the vibration finds application at many places. Now, discussing about the vibration of rotating machines. This is one example. Suppose you have a motor in which there is a rotor, and this motor is mounted on a base plate which is supported by springs. If the rotor is unbalanced like this, that means mass is concentrated not at the center of rotation but at this point, then there will be a force present here. This is with the amplitude of the force coming on the springs will be F max is equal to m times r omega square, where r is the eccentricity, r is the denotes in unbalanced. Static deflection will be equal to Fm divided by K, and dynamic deflection will be given by Xm amplitude of the dynamic deflection will be assume that there is no damping, so this will be Fm divided by K 1 minus omega by omega n whole square. If omega n is very small compared to omega, then this term will become very small. That means Xm the that motor vibrations will be less, and also if omega n is smaller than omega, vibrations will be out of phase. Out of phase means when the force becomes very high, that time the deflection is less. When the force becomes less, then the deflection is more. This type of phenomena occurs in dynamics, which is not found in the statics. Okay, that force is more, but the deflection is less. Force is less, deflection is more. So we say that this is the out of phase vibration. Now, similar type of that 1D that problem can be studied here, that is called whirling of shaft. Whirling of shaft. Now this shaft, assume that you have supported a shaft between two simply supported bearings, and the shaft is rotating, and there is a centrally mounted rotor is there. However, its CG does not pass through the axis of rotation. Instead, CG is at a distance of E. E is the eccentricity of the rotor. Now, this is in the static situation. The eccentricity is E, the shaft is supported on this thing. Now, supposing the shaft starts rotating, then because of the eccentricity, the centrifugal forces get set in. They apply a load at the central of the shaft. As a result, the shaft gets deflected. However, when a simply supported beam is subjected to transverse load, it undergoes elastic deflection, and as soon as the force is removed, it recovers its original position. So, a restoring moment the force is developed because of the elasticity of the shaft. So, when it is rotating, then let us say this is the axis. Okay, this will be this is simply supported in bearings. This may be like this. Then this shaft bends like this. Therefore, the rotor may move here. This is G and this is E. So, this is E, and let us say this distance is R. So, M omega square E plus R is the net centrifugal force acting on that, that is on this m omega square E plus R, and the restoring force is equal to K times R, where K is the equivalent stiffness of the shaft, because it has displaced by R, so it is K times R. Therefore, you get the relation omega square E plus R is equal to K by M into R. K by M is equal to omega n square R, where omega n is the natural frequency of the system. Therefore, R is equal to omega square E divided by omega n square minus omega square, or it can be written as minus E divided by 1 minus omega n by omega whole square. If the operating speed omega, if operating speed omega coincides with omega n, then R will tend to be infinite. So, the condition of resonance will occur and the shaft may break also because of the excessive vibrations. However, if omega is much larger than omega n, then R omega n by omega tends to 0 and R tends to minus E. In that case, the shaft will bend in the other direction, and therefore, this will in fact bend the other direction, and this disc will shift. So, therefore, the distance of the disc from here is R plus E. In that case also the distance will be R plus E, but minus E plus E is equal to 0. Therefore, the disc's mass center will always be at the axis of rotation and a stable motion will be obtained. So, therefore, the operating frequency can be kept higher than the natural frequency. However, at some other frequency, other modes of vibrations may exist that we are not going to discuss here. Okay, so, this is about that. The other point which I want to discuss here, that we have discussed about the vibrations of spring mass system. Now, the spring mass and dashpot system is the most commonly employed that system for studying the vibrations. Here this is a dash board, this is mass m, this is K, and this is C. The equation of motion is mx double dot plus Cx dot plus Kx equal to F. Now, if f is equal to f0 sin omega t, in that case this will be f0 sin omega t. This is a second order differential equation. So, the systems which are described by this are called second order systems. First order systems are described by the differential equations of the first order. Zeroth order systems are described by systems of zero order, that means no derivatives involved. Here it is a second order system. Studying this equation or the solution of this can help in understanding other things also. The similar type of thing occurs when you have spring, there let us say there is voltage source here, you have inductance, capacitance and resistance in the electrical circuit. Here in this case, if Q is the charge, then you have the differential equation equal to LQ double dot, which is basically L times di by dt, where L is the inductance plus R times Q dot, that means basically R times I, plus Q by C. This is equal to Em sin omega t, where this is the voltage, AC voltage, that is Em sin omega t. This is the equation commonly used in electrical and electronics. Now, compare this equation with the equation of spring mass dash part system mx double dot plus cx dot plus kx equal to f0 sin omega t. Instead of the force, sinusoidal force, we have the voltage. Instead of x, we now have variable q there charge. M is equivalent to inductance. It behaves in a similar manner because in differential equation the coefficient is same, its behavior is also similar. Because of the inertia, body takes some time to respond. Here also the same thing happens. Because of the inductance, there is some time to respond. C is equivalent to R. C causes energy loss in the system, R also causes the energy loss. It is dissipative, here also it is dissipative. K is analogous to 1 by C. Capacitor is like spring. Spring stores potential energy and at times it releases. Similarly, the charge is stored in the capacitor and then it is released. So, therefore, you can have the analogy between these two. Similarly, other systems, and the any development made in one field can suitably contribute in the development of the other field. Now, we have been talking about damping. it is difficult to determine damping. Spring stiffness can be easily determined. Take a spring, apply some force, see the deflection, force divided by deflection gives the stiffness. However, damping is not so easy to determine. One method employed for finding out the damping of a single degree of freedom system is like this. Plot the displacement x versus time. These plots will be like this. We will see that its amplitude keeps on decaying, and as we discussed, it is x0 e minus c by 2m times t. One can take the natural logarithm of the ratio between the amplitudes xn divided by xn plus 1, that is equal to 2 pi. It can be easily shown that it is equal to 2 pi c by cc, where cc is the critical damping, divided by 1 minus c by cc whole square. Or if the damping is low, then under root 1 minus cc by whole square can be treated as equal to 1, and therefore this becomes equal to 2 pi. This is the damping factor. Therefore, by measuring the ratios of two consecutive peaks, one can find out the damping. This is called logarithmic okay, this is decrement, logarithmic decrement. In practice, the ratio between two consecutive peaks may be small and may be difficult to measure. Means it can create measurement accuracy problems. Therefore, one can take the ratio of first and k plus 1th peak, or n and n plus kth peak, and then the logarithmic decrement will be 1 by k ln xn divided by xn plus k. It can be shown that 1 by k ln xn divided by xn plus k is same as ln xn plus 1. This can be easily shown. So, it is better to measure the logarithmic decrement based on the measurement of first, say, one peak, and after that 4-5 peaks ahead. So, this is about the logarithmic. Here we are assuming the viscous damping. One can as well take other type of damping. One is called Coulomb damping. Coulomb damping, that is damping due to dry friction. This damping is not dependent on Cx. Therefore, damping force is not equal to Cx dot. Instead, it is constant, that is equal to F. So, that type of damping, so therefore, there will be change in the differential equation, and these problems can also be solved. Okay. Now, I will give that one small example of this one of solving. Suppose, let us do one problem. This is a taut string. This is a, and here you put a mass m at the middle. Taut string. Now, when you displace this object by displace the mass, so that this angle is theta and this is mass m, this displacement is x, then the vibrations start. Now, the governing equation for this case is m, this is the mass, and let us say that this will be equal to L by 2, x is equal to L by 2 theta double dot, that is, this is basically x dot, because x double dot, x is equal to L theta. So, x double dot is equal to L theta double dot. Therefore, equation becomes m L by 2 theta dot dot. Now, this is equal to T, this tension of the string is T. Assume that there is no change in the tension is directed here, T sin theta. So, it will be minus 2T sin theta, However, if theta is very small, in that case this can be written as mL by 2 theta dot is equal to minus 2T into theta, or theta double dot plus 2T divided by m L by 2 theta is equal to 0, and this is again the equation of equivalent to spring mass system, mx dot plus kx equal to 0. This is in this case the natural frequency will be proportional to T square root of T, that means omega is proportional to square root of T. So, more tight the string, more is the frequency, and also omega will be proportional to 1 by root m. So, you see that we study the spring mass system because other systems also generate the differential equation in that form. So, therefore, this equation becomes very important. Of course, here we have considered only the linear system, linear differential equation. Here k is not changing, is not a function of x. If k is a function of x, then the equation will become non-linear and you will get non-linear vibrations. Now, similarly, that is, other cases are like this. The vibrations of the floating vessels. Assume some container or a ship which is like this, and it is in water. Up to a certain distance it is submerged, and then this one. Now, if there is this system is displaced, supposing you give some apply some force here, so it gets displaced, then its center of gravity and the center of buoyancy shift. So, if the restoring force is more than the disturbing force, then it will be able to come back and start vibrating. Otherwise, if the restoring force is in the same direction as the disturbing force, then it will become unstable and it will not be able to come back. If the restoring force is less than disturbing force, then also it will not be able to come back. Therefore, for stability, the restoring force should be equal to more than the disturbing force. Then it will be called stable. Now, once any object, so this is so far stability of, so there also you will, but however that when it goes to the equilibrium position, it by that time it attains some velocity and therefore it goes on the other side. Again it tries to come back because of the restoring force and the vibrations start. So, there will be some vibrations. In fact, when the system is stable, then the vibrations of the system will be occurring. Say for example, now you have this is spring mass system. This is K. Now, in this case, if you disturb it from the position, the restoring force tries to bring it back. Therefore, the system is stable. However, there are vibrations present in the system. Suppose you apply a force which is more than the spring stiffness, then the system will not be able to come in the original position and the spring will break. So, this is the thing. So, stability Now, if K is more, then there is more, it is able to provide more restoring force, and therefore, it will try to bring it quickly to the stable position, and therefore, the frequency of vibrations is more in this case. Back to the original position slowly, and therefore, the frequency of vibration is less. Now, the lastly, we have discussed only single degree of freedom system, but let me just do the simple example of a 2 degree freedom system, so that you can understand that this can be easily extended to multi-degree freedom system. Consider the motion of this x1, this is x2. There are two masses m, both are of equal mass, we are just assuming it, and then this is the spring stiffness m. Let us write the free body, make the free body diagram of this mass. So, this is mass, and then there is a spring force, that is K x1 minus x2. So, the equation becomes mx dot dot is equal to K minus K x1 minus x2. For the other mass, the equation will be mx dot dot is equal to minus K x2 minus x1. This is x1, this is x2. These equations can be solved by these are the two coupled ordinary differential equations. This can be solved by assuming that x1 is equal to A sin omega t plus phi, and x2 is equal to B sin omega t plus phi. When we put these equations, this type of this thing, we will get, we can obtain two frequencies, and this becomes basically a eigenvalue problem, which we will not be discussing in this lecture. Okay. So, this is but the same thing. So, therefore, essentially by solving the differential equations, you can study the vibration. In this problem, there will be two values of omega which will provide the solutions, and these will be called two natural frequencies. So, therefore, in a multi-degree freedom system, you get many degrees of freedom. If there are n degree freedom system, then you will get n equations. So, this is, so therefore, the concept taught here now can be easily extended to the multi-degree freedom system.